button. Okay. Perfect. So let's share my screen. And you can see my screen.
Yep.
Great. So I'm going to sort of walk through the slides, and I have opened like a bunch of tabs for notebook servers, for the documentation. So, if you have any like thoughts, we can just like try things out, and let's just see where we go. Okay, right. So like I've already mentioned in Discord, that I'm not going to cover the entire manual right now. I'm only going to cover some part of it, and I'm leaving the rest for the next sessions because I think it's well chunked that way. Okay, let's start. Generally, right. So what is it? It's a new programming language. The tagline is for AI developers and all that, but really there's more to it. Even though the marketing is just AI right now, I would say it's a more systems language, systems programming language, and it can be highly performant. And the nice thing is that you get the ease of Python, you get the performance of C++ and Rust. That's the promise. And you can leverage the entire Python ecosystem. So why do we need a new programming language? I mean, do we need a new programming language? I'm going to skip this bit because I'm assuming all of us here are interested to see what this is. I think if you follow these two links, you will get like 90% of why we need a new programming language. It's up to you after that, of course, too, if you want to really think on whether you need a new programming language. So some of this stuff, I have pulled out a lot of terms directly from their, what do you say? From their website and all that stuff. And I thought this was a bit, ridiculous on the first page, like compiler technologies with integrated, like this is the marketing stuff, right? So we can gloss over it. So I'm just gonna make some, like hedging myself a little bit here, saying it's a new language. I'm probably going to be like telling you completely wrong things, and my analogies might be really terrible. So the moment you find that I'm wrong, don't come back to me and be like you did this. Just assume that I didn't know it, and it's gonna be fine. All right, so we can dig into it. So Mojo, what is Mojo, right? Let me actually disable this thing. Right, so Mojo, it's a new language. First and foremost, it allows you to sort of use the entire Python ecosystem. That's the promise. And whether it does or not, like, we can't quite tell because it's not fully open yet. But the goal is eventually it wants to be a superset of Python. So everything that you can write in Python, it will run in Mojo. It plans to preserve Python's dynamic feature, and then it adds new primitives for systems programming. So imagine you could use Python and then you add new things to it, and then you can do like really fast systems level programming. The whole idea is to mix this dynamic language world and bring a little bit of like static fast systems language. Notice that they don't say static language, they say systems language, because what they really care about, every time you see systems language, I would say mentally you can think like a highly performant language. They don't talk about like static versus dynamic too much, but this is sort of the differentiating thing that they're going for. So the idea is unified programming model means basically you can do dynamic Python duck type like things, and then you could use it for scripting, you could use it for applications programming like web servers and stuff. You could use it for systems programming, a bit more faster things, and then you could use it for like different kind of hardwares. Like you write the same code, and the promise is that hopefully you don't have to change your code. If I'm speaking too quick, it's probably because I have a lot of slides. So I'm just going to try to get to the part where language starts. So yes, some more, PSA here. I took this straight from their manual. It's just not there today, right? Like it's kind of like clickbaity, but the idea is that I played around a little bit. It's early days. The documentation is a bit lacking, and you really have to be able to like pull out your systems programming hat to be able to get, I would say, anything complicated done right now. All right, so let's dig in. And like I said, we will not be covering the entire manual. I will stop right before this section that says parameterization, compile time programming, because I think that is a lot of fun, but it will be nice if we like spend this time learning the like basic building blocks and then have a really good mental model. And then the next time around, we can come and add more, genericness to things. So, right. The whole idea is that Mojo lets you, like, this is my understanding, right? Like you use Mojo and it can switch modes. Like I was trying to find an image where I could like have a crowd where everybody's doing stuff. And then you bring like a small bunch of people in the crowd who are highly precise, highly performant, highly fast. They get the job done and they move out of the way. So that is my mental map. Normally it just acts like Python. And when I say acts, I mean semantically, it doesn't run like C Python. It has its own, of course, like VM and whatnot. But when you invoke the right like spells or Mojo, right, it switches into a whole different language. Now let's dig into these bits and see what the building blocks are. Okay, where do we begin? Mojo is based on some technologies called MLIR and LLVM. And this is something like Chris Latner worked a lot on. He basically kind of, I would say, started these projects. Basically, what you get out of this is that you get like really like cutting edge compiler, a good code generation system, good control over data stuff. I mean, long story short, like you get these really cutting edge tools, very sharp knives that you can like cut things very precisely. But in modern languages, like in things like Python, we don't want to think about lower level details. We don't want to think about where is memory, how to get things. So the idea is Mojo is going to build these little things below on the surface, and you should be able to use higher level abstraction, similar to Python, and still get really good performance. So that is the promise, right? And this is the first building block, like kind of we can get into, which are these two keywords. So, Mojo is trying to be a superset of Python, which means it is going to include all the keywords you can use in Python, and it's going to add some more, right? And this more part is what I am curious in, and I think that is how you switch modes. So basically, by becoming a superset of Python, they add more things, and then we get the benefit out of it. So two new keywords, like I think this is the fundamental block. It also follows this in the manual itself. So let and var, if you're used to functional languages or anything that has tried to become like functional languages, let and var basically is a way for setting variables in a certain scope to be either immutable or mutable. That is really the gist of it. There's some other things that you can do. I mean, types are used, and I think like I should probably mention this. Like if you're coming from a language like TypeScript, types are used there so that you can build well-typed things, well-typed APIs that interact with each other and don't break. But another one big benefit of using types is, especially on a systems language, let's say like Rust or Mojo, like by specifying types, you can tell the compiler how big things are going to be, how much the compiler needs to, or the runtime needs to walk around to get data. And if you can tell exactly how big things are going to be, compiler can find a way to make things fast, right? And this is where Mojo is focusing on. Like there is type safety, but under the hood, what really matters is performance. So yeah, let allows for like late initialization. You can get an error and sort of. So this is the part where I was thinking, do we want to try this out right now in the notebook, or do we want to go through the slides?
Depends how many slides.
I would prefer maybe you can try it out.
Yeah.
So like it might be a bit slower, but that's okay. So I have a Mojo server running here. Right, let's start this. And I mean, yeah, stuff. I mean, this. So the idea here is like, once you've already defined let being something, at this point, it is immutable. So you cannot reassign it to something else, right? And this is sort of like, while with var, once you assign something, you can keep updating it over that scope. So this is the way where you get out of Python and specify more clearly, like, this is something that I want to change, this is something I don't want to change. So, very basic stuff, but there's a couple of things, and I've written it down on the slides. You can look at it later, but the details don't matter that much, I would say. This is just the building block. The next important bit is a struct type, and people, if you look on Mojo forums, people are complaining all around about, like, why are there no classes, why are there no objects? Like, well, these are Mojo objects, like, you don't need classes. You can go pretty far with like just structs. What is a struct? So struct is a higher level abstraction for defining data access. Really, that's what it is. Like, you want to bunch a couple of things together in one package and make it available to functions, whatever. That is your struct. You can put anything inside a struct, right? And like, for example, an integer itself is a very simple data type. But let's say if you have a idea of a thing that needs an integer, a string, a something, you all make that a struct, similar to how you do things in classes. What you can do, similarities with struct and classes, is that you can define methods on them, just like you do on classes. You can define fields. Operator overloading just means that you can have multiple definitions for the same operator. And then you can do Python style decorators. That's the similar part, but I think the non-similar part is where, the boundaries of Mojo becomes larger, right? So this is
Suvash, this is in addition to the Python classes, right? Because it's a superset. So Mojo brings this as an extra construct, right?
Yes, that is the idea, but as of now, I think classes are not supported in Mojo. They will be, that's what they've mentioned, but right now you cannot use the class. But with their promise of being a superset, and this is where it is not there yet, right? Because on their manual and everything, it's written that this is a superset of Python. And then if you come in with that expectations and you don't have the class keyword working, it's like, what? But eventually, right now, it doesn't work.
But by the way, it feels really like Swift, where you have this classes and struct with really similar, like the.
You're really breaking to this, Stefano.
You're muted.
Yeah, sorry. Oh, sorry. I would say that this class and struct thing is really like Swift language, like old Latin language.
Yeah.
Really,
I mean, this is, like, if you've been playing around with a couple of languages, this is like standard recipe, you would say, of increasing complexity. Most of the time, you don't need classes. But yeah, like, okay, structs, Mojo struct versus Python classes. And the idea is that later on, now that we're talking about it, later on when classes will be introduced, they will have the exact same semantics as Python. They will not be Mojo classes, they will be Python classes. This is why these things are separated in a sense as well, because you want to be able to take the Mojo compiler and run it on a Python code base and have everything work. And that way, like, if you had class represent different ideas in different languages, it will not work. All right, so Python classes allows for dynamic dispatch, this like monkey patching, changing things, like basically it allows for like doing very runtime things. And you see, like, I've bolded out the runtime things. Python classes are all about doing things at runtime. Mojo structs are static, like everything that you want in a Mojo struct, you have to define which the compiler will like check at compile time, and then it will not let you add things or change things or modify things. And this might seem like a downgrade, but the idea is that it's trading the flexibility to do random things on runtime for like highly performant, knowing exactly where things are, how to get to it fast. So yeah. Because of its static nature, like this is the slide for the pros, right? So the Mojo will know the exact structure, how it lays out in the memory. It can even like inline the entire struct. So imagine, your struct has an integer, a certain other 32-bit floating point data type and everything. It can just like put that straight in memory. It can map it, and it will know how many chunks to walk to get to where. So it doesn't have to do like a lot of heap dereferencing tricks, which we can talk about in a bit. Exactly. So it does not need to inspect at runtime for all the information that's already there. Right. Mojo struct, more things. All instance, right? Okay. So when you're using struct, this is when you switch to a different language, right? Like I was talking about like Mojo switching modes. So in struct land, you're entirely, fully in Mojo land here, because this is a whole new thing. Mojo will not let you be less strict. Everything has to be strictly defined. So inside a struct, everything has to be defined with let or a var. You cannot have Python style local variables. And all of these things are set at compile time. You cannot use delete to remove things or change its value. There are some things you can do later, but that we'll talk about later. But yeah, struct works very well with operator overloading. You can have different kinds of, let's say, dunder add for different argument types, if that makes sense. More struct things, all standard types in Mojo, they are made up of structs. So this is, I think, like more like a language nerd out sort of thing, is that, okay, is it truly the foundational concept if you cannot build everything on top of it? Because when you look at like languages, they choose to implement some things as built-in and some things on top of it. Apparently in Mojo, the basic block is a struct, and int is in struct down the hood, bool, string, tuple, they're all structs. And they're actually included in their, they say, standard set of tools. I don't know why this word is used, because usually I think of standard library, but I think what they mean is that it comes with the compiler and with the compiler toolchain, and most likely not as a standard library. Standard library is going to be a separate thing. But basically, a bool is a struct, right? Like everything is a struct in Mojo land. That is the fundamental block. So there is capital int versus small int, and I just decided to put this slide in, even though it's very specific, is that this is how you sort of differentiate between what modes you are in. Like, for example, if you are going to have naming clashes with Python, they're probably going to make a more explicit Mojo style version for things that you use very often. So if you were to use capital int, you would get a Mojo integer, which is fast and tuned for like the hardware, whatever you are in. If you use a Python int, then it's going to be doing things Python style, which means, yeah, whatever it means, right? Python int can do a lot of things. Like at runtime, it can check whether it's a, so here's the thing, I guess what I was saying is that, let's say if you're defining a variable, right, in Python, and say it's like within the bounds of a 32-bit integer, and then you keep increasing it in a loop. At some point, your sort of your data type will overflow, but Python interpreter is going to check that, right? And it will be like, oh, I cannot fit more things here, so I'll change the internal data type of this to be larger, so you can keep fitting. Then you can keep increasing. But all this comes at a cost. The cost is that every time Python is incrementing this, it's checking like, is the new value going to fit in this container, right? So this is sort of the comes with extra baggage, and this is the things that will make things slow. In Mojo, you'll say int is going to be this, and if it goes beyond that, and like it will just drop whatever thing increased. So that is sort of like a way to I just use one example of how things might be different. Mojo has a strong type checking. Yeah, I mean, it can combine the Python's like flexible types and Mojo's strict type checks in the same thing. The primary method is to use a struct. And like I said before, the idea is not only for type checking, but once we know that once the type is checked, right? So this is the first part. And this is kind of like how Rust also thinks of types. Compared to, let's say, if you think in certain other languages like Haskell and all that, is that types are strictly used only for type checking. But in systems languages, they're used first for type checking, and then they're also used for like putting things in the right places in your memory layout, in your heap in your like stack, sometimes registers, so that the runtime can be like fast. And right, overloaded function calls. I just briefly touched on it. You can leave your function name without like, you can leave arguments without type definitions. When you do that, it's just going to work like Python. But once you put in the types, then you get the full power of Mojo, which is like you can define multiple function with same name, different arguments, meaning different type definitions for arguments. As soon as you do that, Mojo will start looking for overloaded things and it will resolve call in the Mojo way.
Wait, do you mean that even if I'm not using a struct, if I'm using just Python code and then I add a type hint, that's going to happen?
So this is defined differently for whether you're using a def or a fun, and we will get to that bit, because def is supposed to be more like Python and fun is supposed to be more like Mojo. That context matters, but we can get to that when we get there.
Cool.
Yep. So let's talk about def first. Exactly, this is the next slide, right? So so def is the def that you know. It's the Python def, dynamic, flexible, compatible with Python. Arguments are mutable. You can make a note of that in your head, because we will come back to this quite a bit. Local variables are implicitly declared on first use. So inside a def, you say like blah equals to 4 at random point, and that is how you declare a new thing in that scope. And this can introduce a bit of a mess, like there is like scoping isn't enforced. And the best way to actually really show this, to talk about this, is to just look at one quick example. So if you look at this, and like I don't want to spend too much time on this, but you can define functions like this in Python, and Python will happily not complain, obviously, because it's a dynamic language and all that. But here you see like y is only defined if x is larger than 0. And then you could return x plus y. So this could sometimes run well and sometimes throw you an error. I mean, typical dynamic language stuff, but this is what it means to, the idea of scoping isn't enforced. Like nobody's checking whether this scope is a valid scope. Dynamic languages, once again. But it is great for like, high level programming, like you're trying things out, you're changing things all the time, like, for example, like even in notebooks, I'm surprised there are some things you cannot easily do in notebooks, and it comes from like Mojo being a compiled language. But this is not always great for systems programming, for all the reasons we're like going back over and over, like memory layout and all that. So now fun is the other keyword they have introduced to define functions, Mojo style. And you can think of fun being like the strict mode for define, like, the caller itself, sorry, the callee. So once again, to make things work with Python, you don't have to do anything on the end of the caller. When a caller is like calling a function, it does not need to say whether I'm calling a def or a fun. It can just call it transparently, and Mojo is gonna like do the right thing. So this is entirely put on the function definition side of thing. And now function has the following limitations or strict constraints, however you like to see it. Argument values default to being immutable. And what I mean is that, the function arguments that you pass in Python, when you use def, there is this thing that some values are passed as immutable and some are passed as mutable. This depends on the data type. And sometimes you can do the mistake of changing things inside and it will be reflected way far out. But in Mojo, everything that you pass in is default to being immutable. You can change the nature later, we will touch on that, but it's like everything that you pass in is immutable in that scope. So yeah, like argument values require a type specification. Yes, you have to specify types when you are in fun. In def, you don't have to. In fun, you have to. So this is sort of like answering your question, right? That you touched on. I hope that makes sense. Yeah. So exactly. So when you have a missing return type, then this is interpreted as a none instead of an unknown return type. This is a tiny detail that matters in some languages, especially functional type languages. Like if you do not specify a return type, your compiler will even complain. In Mojo, they have tried to be a bit more less pedantic, and they're like, okay, we will just return this none. So implicit declaration of local variable is disabled, like, so you cannot just say blah equals to 2. You have to say let blah equals to 2 or var blah equals to 2 inside fun. Inside the def, you can mix and match. Raising exceptions. Now this is cool. And if you've been using like language like with optional types like Swift and stuff, this will, in Python, you would raise an exception and that would just like blow up the stack and go up and catch. In Mojo, and I have not seen this in example yet, but what this means is that you have to specify if a function raises something in its type definition itself. So you have, like, if something is going to throw an error, you have to say that it throws error, or your types won't compile. Very similar to Rust. So, right, let's see. Exactly. Now, before we jump into the further section, like, I think it's worth talking a little bit about this idea called value semantics and reference semantics, because now we kind of slowly get into the more, we have the basic blocks. Now we're going to get a little bit more into like, how do you change things? So if you cannot change things, how do you change things, right? Like this is like kind of setting the stage for that. And value semantics, reference semantics, how familiar do we feel about this idea? How much do you want me to like sort of talk about it?
Can you maybe talk in a beginner way, because
Sure.
I don't know anything.
Yeah, okay, that's perfect. That's perfect. So, like we have two ideas here, value semantics and reference semantics. In the and the word semantics is really used. Let's say when talking about programming languages, you can spend all day talking about the syntax and what it looks like and how things flow. But what really matters usually is how the runtime has implemented it and how it kind of forces it. And this is the part where semantics matter, right? This idea is basically semantics. And now if we get into the difference, the beginner friendly way is, when you think about value semantics, think about the content. And I will give an example. In reference, think about the container, right? So what we do care, let me try to actually pull up a little place to draw things. Perfect. So let's say, you say, I'm going to write like pseudocodey things. So variable, let's say you have a var, whatever. And this is your variable kind of things. This is your objects. Let's say I like var is a terrible word because it's overloaded. So let's just say this is the thing that we care about. And we have value semantics and we have ref semantics. Now what matters is, let's say we want to make a copy of this, and it would make sense in the context of making copy. That's why when you I'm just going to put like a little value inside here. So 42, right? So when you make a copy, or if you look at it, think about the content, think about the container. Now the content here is 42, right? So, and the container here is this whole thing. Now, when you're going to pass these things around in value semantics, what happens is that this value is what matters. So this value will be pulled out, and then it might be, I say might here, it might be put in another container when it's passed around. But what you really get is the value itself. Now, this will make more sense when I talk about references, because what happens in references is that actually no copy or anything is made. Like, two places need to access this. They will each get like a reference of it. They'll be seeing both of them will be seeing the same things. In this case, they'll be seeing like different things. They will each see the value directly. In the other case, they will see the reference to the value. And this is where we get a little bit more into systems programming thinking. Was that kind of somewhat clear, Korean?
Yes, it is somewhat. I think one thing I was thinking about was like when you gave this example was like in C there is this pointer, right? So in this pointer somewhere I have learned like there is this same thing like what you told about like value mechanism and reference mechanism. So
Mm-hmm.
it kind of made sense when I thought about that way.
Okay, perfect. I mean, like people can spend a lot of time just talking about value and reference semantics. There's this really decent blog post that I found on a quick Google search, but I bet if you search on YouTube, there'll be hundreds of videos, like especially in the context of C, C++. So it comes from that part of the world. But the idea is like, why do we care, right? Because there is all this thing, but why should we care? Like this is the part that we care is in value semantics, a copy is made. And in reference semantics, it's the same object, no copy is made. So this is the part that I think you should sort of remember there. Making a copy usually is expensive, and referring to the same thing is usually cheap, but not necessarily. So there's this idea. I also mentioned, let's also chat a bit about lifetimes and moves. Okay, let's do that. Because I don't know how familiar you feel with this idea, but I'm gonna quickly try to drop this lifetimes, because you eventually run into this in Mojo as well. And today we will not be covering the big part of lifetimes. That's for the next one, but we can quickly talk about it. Let's say a value was created 32, and usually in Python we don't have to think about this. Like we just get things for free. Like we're like, what is a lifetime? I don't care, garbage collected, all that stuff. But in Mojo, and systems languages, like garbage, some of them can be garbage collected, some of them are not. So the way, okay, more context. Let's say you have a limited amount of RAM, right? And you want things to be put in RAM, put out of RAM. So somebody has to be cleaning the house, so to speak. You cannot have things for free. And if they're not, then it's going to get filled up. So there is an idea of whenever you create a value, there's the creation. There can be like reads, updates, and deletes. This is kind of like, I'm trying to use the CRUD idea from web, but it's kind of similar. There is some of this stuff going on. So, and this is the whole idea, you create something, you can pass a value to something else. You can make a copy of it. You can say, I don't want to own this anymore. You take it. And we will touch all these concepts in a bit. And you can also say, you know what? The job of this value is done. I don't need this value anymore. So delete it. So with that in mind, we can kind of look more into this. Right. So we get these two interesting functions, like copy init and move init. And it does not matter so much on day one, but I thought it would be a nice idea to just introduce it. So usually in Python, we have init, and that does all the good stuff for you. Like, making the class constructor. It's the constructor definition, right? Sometimes I forget the right words for things. Now, Mojo supports full value semantics, as in other languages. And Python, we will get into that. But let's look into what copy init. I will say, quickly talking about copy init. Let's say when you support value semantics, now you want to be able to make copies. And sometimes you want to be able to say like, I don't care about this thing, you take it, you own it. Therefore, you move it away from me. And this is basically the two main ideas. One is to make a copy, the other is to make a move. If you have used Rust, this might feel familiar, but it's very much similar. And the idea is we use basically these two definitions to control the lifetime of a value. So the lifetime that I was referring to before, these two functions will basically let you tell your Mojo compiler that this is how I want the lifetime to flow. Some of it can be, and what you can do is you can make types copyable, you can make it move only, and sometimes not even movable. This not movable I thought was interesting because I don't think Rust or any other language offers this right now. You cannot just say, I don't want this to be moved. I created it here, it has to stay here. In Rust, and I guess maybe I will get into that at some point, you have to Yeah, maybe. And this is the part where I could be wrong because I haven't looked at Rust in a while, but you have to be able to say either this is movable or borrowable or some other thing. But this is very interesting, I would say, because this can also let your compiler to do even more optimization. If your compiler knows that this value does not need to ever move, which is kind of like defining a constant, but in terms of lifetimes. All right, I'm maybe like blabbering too much, so just like slow me down if I need to. There's a lot more to go through, so okay. So the next stuff is we will now slowly get into like Mojo territory. The idea here is that we'll talk about argument passing, because almost everything in Mojo happens through like passing things in arguments, and this is how you like kind of control the ownership of an object. And I say ownership because I think like I've dropped in little hints of being able to copy things, move things. So the idea with ownership is, in non-garbage collected language, when you create a value, it has to belong to somebody. It cannot just live out there not being claimed, because the moment it's not claimed, it's actually kind of thrown away.
When you say somebody, do you mean like a function? Or
yeah, a scope, actually, more than a function, it's a scope, right?
Okay.
Usually the top level nothingness is also a scope, right? So it has to be in some context. That is what I mean, a function scope. Usually it's a function though. So exactly, the whole language is function calls, basically passing arguments to functions. Like this is the entirety of like Mojo. And a lot of behavior is implemented with like magic calls. And in these magic calls, the ownership is determined with argument passing. This was the short reference to copy init, move init, the magic methods. Now let's compare Mojo and Python. And I think like hopefully this will clarify things, because sometimes like this kind of talk can feel like a bit abstracty and not make sense. So in Python, all values that you pass to a Python def, you just reference semantics. And if we go back, oh, I deleted that, but I can draw it again. Is that you have a value. Let's say this, okay, actually, let's try to do a better job. I will say, let's say this is a function. You created a value here, and then you called a function with this value, right? Now, let's say this is the scope. This is the scope of function. Now, function is starting to happen. This value actually, surprise, surprise, the value does not sit there in Python. It usually sits somewhere else in a place called the heap, and we can like kind of get into it. The value is actually here. I don't want to get this wrong. So the value is actually here, right? So when this function starts running, it actually, both of these are referring to this same thing, right? So the function actually, they're using reference value mechanisms. They're not making copies. They're not borrowing. They're just looking at the same thing. There's a big space of memory. Things are put there. And both of these things look at more or less the same thing. And I say more or less, so I get some room for making mistakes. But yeah, all values passed into Python, they use reference semantics. This is the heart of Python. All values passed into Mojo, Mojo def. Once again, in Mojo, you can have def. That uses value semantics. And this is where things are a little bit different, right? So Mojo actually is not going to be happy with this. Mojo will actually say, okay, you want this value, you know what? I will make you your own copy. Maybe it's not in this yellow space even, actually, to be honest. That doesn't matter. What matters is that by default, they'll be getting a copy of that. So the function receives a copy of the arguments. It can modify arguments, but will not be seen outside. This is by default, once again, okay? Like not all the time. If you don't specify, and we will get into specifying this different things, but if you don't specify any special keywords, then in Mojo, all the arguments that you pass will be like a mutable copy. So anything you change inside is not going to be reflected outside. In Mojo functions and Mojo funs, they're immutable references by default. So once again, looking back at the same thing in Mojo, and let me draw another one for Mojo. And you know what? I will put actually a lock here. And there's no lock up there, right? So in that case, it's going to be kind of like this. So it's going to be a reference, but you will not be able to change it. And there's some good things to it. The thing is, there will be immutable references. Does it actually work the way I showed you? Probably not, because the compiler can do tricks where it's actually behind the scenes still gonna pass it by pointer, but your code will not be able to change those things. So it will be kind of read-only pointer. I mean, that part is not relevant, but basically in Mojo functions, everything are immutable references by default once again. Now this idea is actually more commonly known as borrowing. And we will get into that. Right. Does anybody feel like they want to take a break or something?
I'm good for now.
Okay.
Sure, good.
Okay, great. Or any questions, anything?
Would you like to take a break? You've been talking for a while.
No, that's okay. That's okay. I can continue. All right. Let me continue then, because it would be nice to kind of go through this more dry part quickly so we can get to the notebooks. So yeah, argument conventions in Python, all fundamental values are referenced to objects. We already talked about this. A Python function can modify the original object, which means that if your argument is a immutable data type, you change something inside the function body, that thing is going to change on the outside. You have to be mindful of this in Python. Python devs are used to thinking everything in reference semantics. So if Python is the way you've kind of learned to code, it might be hard actually to sometimes think of this value semantics, but it's just a matter of getting used to it. But at the CPython level, actually, the references themselves are passed by copy. And this is the detail that does not matter so much. They actually do make a copy of the reference. It just gives a pointer, reference counting stuff. Not super relevant, but what we can talk about is, though, there is a very like fun and quick programming paradigm. You don't need to think about memory, and everything is allocated on the heap. Should we talk about heap, stack, and registers? Like, do you want me to quickly go over heap, stack, register in a, I don't know, somewhat beginner-friendly way? Because I think it's a, or if everybody feels comfortable, then I can keep. So say yes or no. Somebody say yes.
Yes.
Okay.
Yes.
Okay.
Please.
That's all I need. One yes is enough. Otherwise, I just continue. So let's say there are three different things. Just gonna draw three columns. So let's say you have the CPU. This is your cool hardware, whatever, right? Like I'm just gonna say CPU. And inside your CPU, there is like a little, like, there's tiny places to put data. I mean, this is how CPU can get anything done, right? Every time you run function and CPU needs to do something, it needs to actually put data in itself. It cannot go to memory and change things. What happens is that the data is pulled from memory into CPU, CPU changes things, and then it's pushed back out to memory. So there's a little, like, there's tiny places on the CPU. It's called registers. It's super fast for CPU. I mean, because you can guess, it's right there. Like, this is one of the fastest operations that can be done. The next thing is that I'm going to talk is about something called the function stack, right? So imagine your program started running and there was like a queue. Every time a function, let's say we started the program with function A calls B, B calls C, C calls D. Just it's an easier idea. So function A starts at the bottom of the stack, right? It's like the way your Python interpreter, or let's say your Mojo runtime, or we don't think about that. We just think about stack, is that your function starts here, A. It's now to run. First, the Python runtime will put your function on the stack with whatever other metadata it needs to run. And usually this is like arguments, let's say args, right? And in Python, once again, remember, there is this place called, now I'm going to talk about heap really quickly. Once again, all of these drawings I'm drawing, this could be kind of wrong if you're really going to, you know, like be pedantic about it. So this is just for analogy once again. Now in Python, we already know that things are passed by reference, right? So these arguments are not actually put on the stack. These arguments are actually reference to things on something called the heap. Heap is a large space that is initialized every time you start a process. And this space is like, you can imagine like you have a very large desk or a floor, and you just put things there randomly, you know, you don't care so much about it. Every time you need to get something, okay, a better analogy is you working at a desk. Everything on your desk is like super nearby. Everything else is on the floor in the other room. That's your heap, right? You go to the heap and you get stuff. You go to the heap, you get stuff. So every time you need to go to the heap, it takes a long time. And every time you're doing things at your desk, it's quick, right? So like just, what matters is this time it takes. So once again, function A calls function B. Now this is, and function A isn't done yet, right? It just called B in the middle. This is classic, you know, typical program execution. B calls C, C calls D, all that stuff, you know, like we keep, and all these arguments, they're still references, and just, you know, you can keep a mental note that way. Now what happens is once D is done, then it will kind of like, this stack will be like decreased again. And basically when people talk about execution stack, or when your compiler, or when your like, you know, runtime says like stack overflow, basically what it means is that you have called too many functions and there is not enough space to allocate anymore. Therefore, now you're like kind of done with this. The reason I'm talking about all this is that in Python, all this stuff you see is on the heap. Now, wouldn't it be nice if you could put things on the stack itself, right? Like this seems like an obvious like thought once you sort of, you know, think about this. Can I somehow delete this? And that is what sort of systems languages allow you to do. Like when you're writing code in C or C++, you need to think about this stuff a lot, especially in C, maybe not so much C++, but you have to kind of say, okay, this is something I want to put on the heap. This is something I want to be right here. Not everything can fit here once again. So there is a limited space, all that stuff, but you can actually put, let's say, a value right here, like 42 and 33. These are small integer values, whatever, you put it right on the stack. And now you don't need to go to the heap. So this makes your, you know, overall, this, if you think about this properly, this can make your program really fast. And one last trick that Mojo does, and we will talk about, is the Mojo does something like I don't think I've seen in a language before, but I could be completely wrong. There's a lot of languages out there. But at least on a general programming language, Mojo lets you put some of this value directly on the registers. And this is very cool. This is where I do that little like scream, you know, this is cool, sort of, you know, but basically that is heap, stack, register. Really poor introduction to it, but I think like from here you can go and look more into. I think Alex, you shared something on Discord, so perfect.
The caches are in between.
These L1, L2 caches you were talking about.
Yep.
Those are also things, if I'm correct, on the CPU, but they're a little bit. So if we go back to the same drawing, let's make the CPU like a lot bigger, right? Let's make it very big, and then say that the cache is somewhere here. So the registers are right there next to the ALU, pretty close, and the cache is like a little bit further. It's still on the CPU, but it's a little bit further. This is my understanding, and I have to double check this once again. But basically, register is the fastest, and then it's the cache, and then it's your, and then it's the CPU cache, obviously. Then it's your RAM, and then it's your disk, and then the network, and so on. There's actually, talking about this latency things programmers should know. Actually, I was planning to put this on this slide. I totally forgot. Yes, I will share this. This is a great thing. So you see, like, I will share this so you can play around with it. But the general idea is that you can see how some things are so fast and some things are so slow. So imagine one little thing is 1 nanosecond, your L1 cache reference. And this is where L1 and L2, I don't remember if L1 are the registers and if L2 is something else, but they're both in CPU. Then you have your main memory and then network, disk, so on. I will share this stuff later.
Suvash, I had one question.
Sure.
Actually, in your slides, actually, you mentioned CPython uses this the direct value reference, like the same mechanism as Mojo right now uses, or like I meant like the value semantic method, or is it the other thing? CPython.
So this is something you can change, and we will get into that. By
Oh.
default, actually, Mojo lets you have immutable references. So
Okay.
that means that you will be referring to things on the heap, right? On that big space. 2 of your functions will be referring to the same thing, but they will not be allowed to change it. So to give a more better idea, I think it's good we talk about borrowing before we actually get into borrowing, and we can use some more function scoping stuff. This is not getting too long or anything, right?
This is awesome.
Okay, great.
Yeah, good.
So let's say this is a function, right? And you said you made a value here, like let's just call it v, and let's give it, I don't know, 4, 2, 5, 6. Usually your values are not going to be a value, it will be a struct, right? Because everything that is meaningful in Mojo will be a struct. But I'll do this to simplify things. And let's say this is the default. We're in the default mode right now. And I could be wrong, but I'm trying to explain what borrowing is. So don't think about Mojo for a bit. Now this value here is not really here, right? This value is actually in your heap. This is like all that, like it's the next room in your apartment. You can put everything there because it's empty more or less. So it's here, 4, 2, 5, 6, right? This was that function. Let me now call another function here. I'm going to say v let me call another function. Let me call it fv. Actually, it's so easy. You just write an n here, so then you get a Mojo function. Isn't that fun? Sorry, just stupid nerd out. Yeah. But yeah, like, so function calls v, right? And this is your fn. Now what happens is, by default, this function, like I said before, everything you create, these values has to belong to somebody. So by default, it will still belong to this function. So I will put the lock here. So this kind of means that it belongs here. What happens is that this function is going to say, can I borrow this? I promise I will not change it. And it can satisfy the promise by setting things in a requirement. Imagine you're like friends, right? Your friend just wants to like get your Nintendo Switch and not put any games or hack or anything. This is a very similar idea. Another function borrows this. After they're done, they will give it back. Now the thing is, instead of things being given to you directly, maybe there is like a Nintendo Switch bank or something, whatever. So instead it's put there. Somebody owns it, you borrow it, you return it. That is really the concept of borrowing. This was made very popular with Rust because Rust built into the language. It was always there in C, C++. People would do this in sort of like using libraries and their own ideas, but it was baked in the language, I would say the first time, probably by Rust. So does this answer your question?
Actually, it didn't answer my question. My question was specifically about that. In your slide, when you were comparing about CPython and Python, right? Like Python uses this mechanism and CPython uses.
Can you? Okay.
It's after this, I think it seems.
Okay. Let's see. It's probably somewhere here. This one. I think this is the one you're talking about. Everything in
yes.
Yes.
Yes. Exactly. So actually here I was confused because like C Python is basically the normal Python which we use, right?
Right.
If I remember correctly,
Right.
there is Python also. So I was curious whether like what is the default? So it is like is it having the Mojo kind of mechanism now already? I was just thinking that way.
So this is the part, maybe I should have not put the fourth point in there because I know that's a bit confusing, the passed by copy
Yeah.
sort of thing. But
Yeah.
okay, what actually happens is so
No
in
worries.
Python everything is reference semantics, right?
Mhm.
Like which means that it's pointing to the same thing. Now what C Python does is sometimes it actually even makes copy of reference semantics. Imagine
Oh.
there's a tie between this, and this is just like more penalty. This is even slower. If you imagine you're both looking at references, this is also looking at reference, this is also looking at reference, but they're like C Python is making a copy of it, and probably, I say probably because this is the part I don't fully understand, somehow syncing it, and they sync it using things like reference counts and whatnot. But this is the part I don't feel very comfortable. But I guess how you should read this is every time something is passed by copy, it becomes slower. So even like if you promise reference semantics and you're using pass by copy under the hood, then you're not getting the benefit out of reference semantics. That is like, because with reference semantics, you could have been pointing to same things. But that is the promise you made, and you made a copy anyway. So you're just paying the cost for no good benefit.
Got it. Now you made way
Okay.
lot.
Okay,
Thank you
perfect.
so much. Yeah.
No worries. And this is the part, like, I don't know enough about C Python stuff. But
So,
okay.
yeah. No worries.
Right, heap stack register. We're done with this part, right? Heap stack register, I think, is somewhat clear now. Hopefully. You can unmute and just say something to me sometimes.
Yes.
Okay, thanks. Because I think this is the part of presentation on Zoom that I really don't find so much fun, like you talk and then you kind of create this space of emptiness so people can talk back to you, but then people are waiting like, should I say something? Is he gonna say something? Is she gonna say something? And nobody says anything, right? I think it also helps if I had a second monitor so I could see your faces more like large, but yeah. Either ways, back to the slides. So long story short, we do all this heap, this, that, borrow, all that. The reason is that we want things to be fast, and it's really good to be able to have a fast mode in your language. You can say that this car can go faster, so let it go on the faster lane. This car needs to go a bit slower, so let it go on the slower lane. And this is kind of like Mojo will let you do that, while Python is like, no, everybody uses the same lane, same speed, whatever. And like, I'm dropping all these really bad analogies all the time, but I hope it helps. So structs are always inline to their container, whether they're a field of another or into a stack frame. What this really means is that, let's say you have a struct you defined, and struct itself is a box, right? It can contain things in it, but now you can have a struct that has a member, which is another struct. I hope that makes sense, right? And what Mojo will do is that, let's say in some programming languages, what happens is that when this is allocated on the heap, a struct is allocated somewhere here. Instead of using my hands, I'm just going to use this same thing. What inlining basically means is that pen. This is the heap, right? There's multiple ways of doing this. Let's say there is like, we have two struct types. We have A and B. Now, let's say struct A, you defined a value out of struct A. You define another value of struct A. Now, let's say we have struct C, and C has members A and B, right? And if I were to define this on heap, I could do two things. I could do like, oh, this is the definition for C. This is member A. This is member B. And they would use like pointers to know who is where. But Mojo is like, no, we want this fast, so we don't do that stuff. We will actually do C, and A is going to be inside here, and B is going to be inside here. It's going to be inlined. That's the idea of inlining. instead of having reference, it's going to be right there. They'll be right next to each other in memory.
So it will be like assigned a separate value, like it will be kept in the memory itself. C is something which, even though A and B is existing, C is something created separately with A and B in the
Yes,
context of it,
in
right?
it, exactly. So
Got
in some programming language, they're like referred with pointers, like, oh, I have allocated A here, B here, but in Mojo, it's going to be, they're always going to be in that same space right next to each other. And this matters where you were in memory, because once your fetcher, your data fetcher, knows where to find C, that object you created, now it does not have to ask the heap manager where that A is. It knows right there, so it can just walk in the memory space and just get things fast.
It's like disk defrag.
Yeah, exactly, right? Defrag is a great example of thinking about this. Yes, I even was trying to get a screenshot of like Windows 95 defrag something, but I was like, too much analogies. But yeah,
this means that you cannot use, you cannot object reuse, right? So like if you mutate not in the actual local mutation, but let's say you mutate this object by creating another object and just having this subfield changing, you can't reuse the old structure. You have to recreate the entire structure. You have to really copy the entire structure.
So this is for the default mode, right? Like we will see, it allows you certain mechanisms where you can say what part is borrowed, what part is moved, and we will get to that. But you can, so this is the thing, right? Imagine your object does not need to be reused, then you can go on the sort of the fast lane. Now, there are some parts of your object that needs to be reused, or like not reused, but they can be seen by multiple things at the same time. So they will have to be borrowed or copied or something. We can specify that. But what you're saying,
so this is the default is the copy by value. So whenever I need small modification of an object, I will always copy it. This is how it works. And like several defaults, I kind of a little bit lost there. So you said there is a default on the def and there is a default for fn. So which default are you referring to?
In this, when I say struct, it's always going to be in the Mojo, right? So struct is entirely a Mojo thing. It's not present in Python. So whenever they do these like really different strict things, it's always going to be, I guess the way to think about it is everything strict is going to be Mojo. Everything like not strict is going to be Python, more or less. That's an easy way to kind of think about it. And yes, so struct are always inline into their container, whether they're a field of another container or into the stack frame of the containing function. If you remember that stack I was building, so what Mojo can do is it can even put like this ABC kind of struct directly into the frame if it fits. Now this is the thing, it has to fit in the stack frame. If it cannot fit, then you'll have to assign it on memory using pointers. But anything that you can fit, like maybe, and this is the part that I don't know enough, maybe like a floating point 32, floating like 64, long double standard types that can fit in the stack frame, Mojo will put it right there. So it doesn't, your code doesn't even have to go to the heap when it has to run. So, when that stack that you saw, when it like unrolls, the function will be there, the values will be right there. So nobody has to go anywhere. It can just like get to its job right away.
How big is the int struct? Like, do you have memory penalty for besides the 32 bits?
Sorry, can you say that again?
Like how big the struct? You said the int is also a struct, right? So I presume like when it's stored in the memory, it's bigger than the 32 bits, right? So
right,
how big is that penalty?
So this is the part where you and I will have to look at documentation for the built-in types, right? So if we look at int, what is an int? So underlying storage for the integer value. There's multiple types of int you can use. Signed integer 16-bit, 32-bit, 64-bit, right? So depends on which one you use. It's going to, if it fits in the memory, if it fits in the stack, it's going to try to fit it. But I'm assuming all these built-in types, they will fit in the stack frame. Does that answer your question somewhat?
Yeah, I was actually, like like when you have a box, this is like a box, because when you say that everything is a struct, I kind of assume that there is a box, like in Java, for example, right? So there's like, which takes itself space. But I think that will be that probably is not how it works, right? So it's just a concept, right? It's just like abstraction.
Yes.
Around, but internally it's still stored as 32 bits if you talk about int32, right?
Yes, of
So
course.
it won't be stored with an extra box around it.
No,
the box
no,
is
no,
not stored.
no, it will not be. So I mean, yeah, internally, like the box does not exist. This only exists. All these types and everything, they only exist even in type languages at compile time, at the type check time. Once the type check is done, then these types go away. Inside your memory, everything is like laid out in memory, like, you know, there's nothing, no boundaries. It's like the compiler injects code that tells only look at these segments of memory because this is your int value. And then you look at this other memory, and this is done all with like offsets and start bits and whatnot. But these boxes, like in memory, they don't exist, of course. Classes, right? We're talking about classes. Classes, when they're ready, they promise to have the same semantics as Python, which is reference semantics. So not breaking anything there. I mean, this is not going to be practical for small types, or, you know, like the idea is for small types, you don't need reference semantics because guess what? You can put it directly in the stack of the function. So let's just use, you know, structs for those types, like integers. And this probably goes along with what you were saying, you were asking. So a lot of this stuff is also, you know, like I've been going to the manual. There isn't a lot of documentation right now. So there's also some kind of guessing by kind of overlapping your mental map with the other programming language that you know, which kind of is Rust in this space. So all this stuff is also not out there. Nobody has written a book or anything, right? So a lot of what I'm saying could be completely wrong. But I guess the idea is that after this, if you feel comfortable with why things become fast because some things are close and some things are far, then I would say like my job was somewhat well done. So exactly, now your question, right? You were asking, so how do we change things if we cannot change anything? Like this is like bonkers, right? So you can actually have something called argument conventions in Mojo. So with different kind of conventions for arguments, you can change the behavior of how it's going to be inside function. For example, how do you implement methods that needs to mutate in a struct, right? The function, like we said before, a default function that is not defined with anything takes a immutable reference count, which means you cannot even do things like, you know, in a class self dot value equals to 10. You cannot do that because it'll be like, no, it's an immutable reference. So how does this actually work, and how do we make basic things work? How does let work prevent mutation? Okay, Mojo compile. Oh, this is a very generic answer, and we will probably not go into this, but this is how Mojo does all its magic. It does what is called data flow analysis. So the compiler actually kind of flows through your code and sees the lifetime of objects and the promises you have made. Like you've another way to say this is that Mojo looks at your code and then it looks at the promises you have made about objects. You said that you will not borrow, you said you will own, or you said you will copy, and it will look the flow and figure out, is your promise correct to what it sees? And if it isn't, the compiler will complain, right? This is how sort of like compiler like Rust and Mojo sort of do stuff. And I don't know enough about it. Unfortunately, I do not write compilers for a living. That would be cool, I guess. Similar to Rust lifetimes, but work a little. Yes. So this is the part, you know, like every time you look at Rust online, it's like, it's this History Channel guy explaining stuff, you know, like if that meme makes sense. But Rust is like, if you try to play with it, there's a lot of decoration around it. Like you have to put a lot of symbols in the right places and then say a lot of things before your code will compile. What my experience and what it looks like with the looking at the manual is that they have tried to not add too many keywords or confusion points, so it becomes easy enough. You know, you can for most of the time you will not even be thinking about this because the defaults work in the way you want them, and when you want to actually change it, then that is only when you sprinkle in the words that matter. That is the promise, at least. We will see. So there, now we get to the memory ownership stuff. Memory ownership for objects, they're passed directly into the function argument. It has to be defined in the arguments of the function. And we've talked a little bit about defaults. but now we can specify the type of each argument. And maybe for this, it is worth actually opening the manual. Because what I wanted to do is, at this point, I wanted to write some code for it, but I think what is going to be worth is definitely looking here. Exactly. So let me try to just get this to the right place. Borrowed. We will come back and look at code while we talk at this instead of drawing boxes. I don't want to draw boxes anymore because I think at some point this kind of analysis break and it's better to look at code. So we can specify argument like the ownership on each argument as needed. There's 3 types of ownership. One is called borrowed, the other is called in-out, and the other is called owned. And with a combination of this, you can do like pretty complex stuff. So I will talk about borrowed is the part that we've been talking about a lot right now. You know, like, so borrowed object is an immutable reference. Remember, immutable, which means you cannot change. Reference means it's somewhere there. It's not with me, but it's somewhere there. Somebody else owns it and I cannot change it. So the callee is the part where your function was called at. Usually the callee already has ownership of this. It actually owns the value. So the callee has full read and execute access to the object. Oh, sorry. Caller callee. Callee is the function being called. My bad. So the function has full read and write access to the object, but it cannot modify it. To see this in action, let's say what it looks like is you would just write something like this. You write a function and then you'd say borrowed. I borrowed this. This is the default. So if you didn't write anything, it would be borrowed. And if you were to run this function, they would both be pointing to sort of same things. But I just wanted to show what the syntax looks like. And here is something that I just wanted to show a small example. Maybe we can, you know, if we want to hang around after the presentation, we can try to like type a bunch of stuff and see.
So borrowed and immutable argument is synonyms, right? They use it interchangeably.
They play well together, but I wouldn't say they're synonyms, right?
So just in the documentation, I saw that they put borrowed in the parentheses. So I thought that maybe they use the same term.
I mean, immutable arguments are borrowed. That is the right way to think about it. If you have an immutable argument, that is going to be borrowed. So borrowed is sort of like the idea of how lifetime works. And immutable arguments are always going to be borrowed, if that makes sense.
Yeah. Okay. Yeah.
So once again, when you're doing a lot of Mojo on day one, this does not matter. I'm just like going through the manual, you know, and presenting the language because this is kind of like somewhat under the hood. But what matters here is, you know, like this is the part that I think there is a caller and a callee. Let me once again, like just do this. This is one function. Let's say this is another function. Okay, I'm just this function A, function B, a value was created here. Now in this context, this value 43 whatever is created, it is owned by A, right? It is owned by A, and somebody called the function B with 43, and the argument keyword was not defined, or maybe it was defined and called borrowed. Now what happens in this case is that B is going to get to see this. It can see it, it can read it, right? But the compiler is going to make sure that it's never going to try to update it. And this is the part where sort of borrowing also plays in, because what could happen, what you can do, and this is like, why would you do that is a good question. But A could say, B, take this stuff. I don't need it anymore. And it could, you know, B could take over that stuff, but also keep the promise that I will not change this. And if that happened, then it would have been a immutable ownership, right? because, and this is where I don't want to like say borrowed is mutable or immutable. Like those are two different things. One is the promise that you will not change things. The other is who owns what.
B is caller and 43 is callee.
Sorry, this is caller, right? Because your code runs here. And then A is calling B. Therefore, this is the caller. This is the one that dialed the phone, so to speak, because somebody dialed the phone, right? Like if you're the one dialing phone, calling a function, then you're the caller. And the one who received the call is the callee. So if we look at here, the callee, like let's say I call Alex, right? Now Alex, and I said, Alex, the number is 200, whatever. This is the password, right? And then Alex has full read and execute access. Like he can do whatever with that password, but he does not get to change it. You know, I still own the password, sort of. I still have the full exclusive ownership of that object. And this is in the context when Alex is borrowing from me. So the default behavior for FN is borrowed. And this is what I was trying to show here, is that if you didn't write borrowed here, it would be borrowed. That is the default. If this does not feel clear, just somebody say something, because after this we will move into a little bit different, and it would like having this kind of set well is going to play well with the other ideas. If everybody feels comfortable, then I can move on. Yeah, that sounds like the sound of comfort on Zoom. So I'm gonna move on. So basically what I wanted to say, like, see, you cannot just update self values, right? So imagine in this function, right? You borrowed this. And then let's say this was a function on a struct, then there would be self, right? But if you did not say a keyword, which you will say in a bit, and this is what it looks like. It says in out self here. If it's borrowed, then you would not be able to do this kind of stuff. You would not be able to update it because this self was borrowed. If you borrowed yourself, which is like, why would you do that? But forget why would you do that. But if this was borrowed here, then compiler would say like, you are not allowed to change this. And we will get to that part. This is why any place in like Mojo code, when you see in out, that basically means that I'm allowing myself the ability to change things. We will get to in out next. This kind of confused me on day one. You know, I wrote a bunch of code and it didn't. I was like, wait, what? So I was like, okay, let's dig into the manual. Oh, apparently I have more stuff on borrowed. Okay, why do we care about this, right? Like all this mess, which it probably might feel like right now. Does it feel like a mess? Nobody's saying anything. So come on.
No, it's fine.
Okay. Yeah, feel free to unmute and say things. But yeah, immutable arguments, why do we care? It's very efficient when we pass large values and expensive values, but because the compiler knows that, hey, this thing is not going to change this, which means I can put this closer to something and far away from something. And it can do like optimization tricks, right? And the copy constructor and a destructor does not have to be invoked. Look, it can just like short circuit this. So if you're never going to like update a value, then why even bother with the copy in it? The copy in it will never be run, so it can get rid of that part. And there is another destructor, which means that when a function is done, it will call its destructor to make sure all the things it defined were thrown away. It doesn't even have to call that because this function did not like create anything. It only borrowed. You know, this is the nice thing. Like all the ownership is like, if we go for the same Nintendo Switch sort of reference, if Alex owns it, I just borrowed it. I don't have to care if it breaks or, you know, if something happens. Like Alex is fully responsible. So I can be like, you know, very chill about it, I guess. I should not borrow like that, but you get the idea. So implements a borrow checker that prevents multiple mutable references to the same value. So this is the tiny detail. And if this does not make sense right now, it's okay. We can just come back and look at it. So you have a value in the same drawing. Let me just draw it. Let me just draw it. So this is your value. Let's say there is 3 different places that want to use this. Then they're all saying like, "Oh, I want to borrow it." If all of them want to borrow it, which means they're gonna have read-only copy, they're not gonna change. This is fine, right? But if A said, "I want to borrow it," B says, "I want to borrow it," and C says, "You know what? I want to change this," then this falls apart, because you know what, like, and this is where it can be fun to learn a language like Rust, because they really bake this in the language, is that if A says, "I have a read-only copy of something," B says, "I have a read-only copy of something," and C can change that anytime, then the entire data contract breaks down. So the compiler is going to be like, "No, this is not a valid thing. I will not let you do this." Like this kind of things are not allowed. So you'll have to figure out other ways to, get your things done. So multiple borrow is okay, but as soon as there is a mutable reference and a borrow at the same time, the compiler is like, you're saying like somebody is borrowing this and somebody else is changing this. Like you cannot change things under this is not even allowed.
May I use an analogy? I don't know if it will work for this.
Sure.
So think of password sharing, but only one person has the 2-factor authentication code. Does that work? So you have your caller who has this 2FA, and then all of these different callees have
Right. So
the password, but none of them can change it except the first person.
Exactly. Like if you were to, in the same context, imagine like you're in an organization, you have like a shared password thing, like Bitwarden something, and maybe there's an admin setting that says people cannot change this, but they can see it. That is effectively borrowed. So they get to see it and they get to do whatever with it, but they don't get to update it. I hope that makes sense. Instead of 2-factor, it's like, it's not even that, it's more like they literally do not have the permissions to change it, only to view. So it's a read-only access, really. Okay. So, yeah, and then a tiny little detail, small values like int, float, SIMD. SIMD is going to come up a lot when you look at the documentation. It stands for the name is called single instruction multiple dispatch, and we will not get into it a lot because frankly I don't understand a lot of it. But the way CPU works, like a lot of CPUs work, is that you give instructions to CPU. You say add one thing and another thing, multiply one thing and another thing. But sometimes what you can do in modern CPUs is that you can say there is this complex instruction, add this, multiply this, and then put it somewhere else. So this is the single instruction multiple dispatch part, which means that traditionally CPUs could only do one thing in one instruction. In modern CPUs, you can do a lot of things in one instruction. That is what SIMD is all about. And if you can make your code do that, then you will run much faster. You will actually use SIMD in the CPU. And Mojo is like, on day one, it can do SIMD. In Python, if you had to do this, it's not baked in the language. So most likely Python does not use anything SIMD. But this means that long story short, you can make use of advanced hardware. Like all our CPUs, they have like this multi-core, multi-whatever SIMD, but very little software actually makes uses of this.
Is that because it's a new thing?
Yeah, it is sort of not so new anymore, to be honest, but it has been new. And I think this is where the part is that, Python came out in the 90s and SIMD actually matured much later. I would say probably 2000s, maybe later. And, like SIMD is such a low level thing as well. Like it's literally a machine instruction that says, I looked into this stuff once, but now I forgot. But long story short, usually you can do adds, multiplications, jumps. In SIMD, you can say like, add this, while you're doing that, also multiply this, and you will do it in the same cycle, clock cycle. And you have to, your Python bytecode interpreter has to somewhere make use of SIMD instructions when doing these things. And if it doesn't, then it doesn't. So there is no way for you as a Python programmer to say like, I want to go and use SIMD primitives, because it's like assembly language stuff.
But I assume there are some trade-offs. I mean, people in Python also want a fast language as well, right?
Yeah. I mean, SIMD is not useful everywhere. Like I have to say that, like, right? Like if there is no point for doing single instruction multiple dispatch, why would you do it? But SIMD makes a lot of sense when you're doing like additions and multiplications, and you can do a lot more faster things. And like tensors and Mojo is all about like tensor operations. So there it really shines. And I bet like Julia probably also does some kind of this stuff using, LLVM and all that. But you will see a type that is literally called SIMD. And I'm like, in my mind, it's a way CPU works, not a data type. So I also have to like look up more and try to understand this. But let's say if you decorated your struct with register passable, then it's going to directly put it on that CPU register. If you remember from the drawing before, it will not even be on function stack. It will not even be on the heap. It's going to be directly on the CPU or your accelerator. Right, a quick borrow, Rust versus Mojo. There is a little bit of difference probably in Rust and Mojo borrowing once again. Maybe it matters, maybe it doesn't. In both cases, this is the part that you should care about. Borrow checker makes sure that you're fulfilling your promises. Mojo does not require a sigil on the color side. So in Rust, when you're borrowing, you have to put like an ampersand or a star or whatever. Think like you put one more character to say that this is passed by borrow. In Mojo, you don't do this. You define it on the function, and this is sort of the ease part that we're talking about. So Mojo actually makes uses of this machine register, which I don't think Rust does either. Like, it does not put things directly on the CPU register. And don't take my word for it, but I think this is correct. Rust defaults to moving values. Like if you've used Rust, every time you call a function, you're like, take this, I don't want it. Basically every function is like trying to give things away to somebody else. In Mojo, it's passed by borrow. That's the quick thing here. This is the part that is our bread and butter in Python. It's called in-out. And I will quickly, this is what it looks like, in-out. This is a term, I was not familiar with it, but like if you're a Swift programmer, and this is why I wanted Pedro here, because Pedro has done a lot of Swift, it would have been cool to see like what he could bring in this discussion, because I bet there is a lot there. But in-out basically was an idea that grew from Swift community. And in-out basically, I was like, why is this word so weird, right? Like every time you see a new thing, like instead of thinking it's weird, if you try to understand why it's defined, it helps. It's a very like intuitive idea. So changes to the argument inside the function is made visible outside the function. So think the same thing, caller, callee. I already erased that. Maybe I should have kept moving the drawing board around actually instead of deleting things. But either ways, whatever you change inside the function, it's going to be reflected outside. This is how you can do things like finally update stuff. This is a struct, we have a value, we have a function. This function can finally change something in the scope of self. Also for non-trivial things, I mean, you can also do in-out for like non-trivial things, as in not just like integers, but you can also do it for like array subscripting. So you can, let's say, define a struct, a member of a struct, and say, I want to change the row number 2, column number 3. You just have to write more code. That's all. Not called pass by reference. Even the in-out convention is the same. Okay, exactly. So in languages like C, this used to be called pass by reference, because literally the same reference would have been pointed and you would update. It is not called pass by reference in the documentation here, because the compiler under the hood actually may pass values using pointers. And at this point, that is all the information we need. I just quickly put it here so you don't mix it up with the idea with pass by reference. It's not the same as pass by reference, but it's not super important either. What matters is that we can update things inside and it will reflect outside. The final thing is owned. And owned is where if you remember, I said before that there was like a caller A. Let me do this. This is B. So we said like, we created a value. Sorry. we created a value here, something 410, and then like, when we called B with 410, this could be a struct. If we can design this thing in a way that B takes it over. So if this was V here, so B takes it over. Once this function is called, like, then you get 410 here, whatever, not the same color. You get here, and effectively it's removed from here. So later, if you go down and try to print V, like there is no V here, like it does not exist. And this might be even if it feels like a tricky idea, if you're using Python, just think of like how this works in memory. Like it's literally given away. So when you give it away and try to use it here again, it will not work. Rust programmers on day one, this is the issue. You try to write any Rust program, you call a function with it, and then the compiler is like, no, I don't have it. So this is where you say like, B has taken over the ownership of this value. And that is specified by using the argument owned. So if I go further down here, inout, we already addressed it. Inout is the usual stuff. Owned, what it looks like is, so this is the function, right? The function that takes the ownership is going to define the argument as saying, I will own this. And on the caller side, that function will have to be called with a little, what is this thing called? Superscript? Hat? Whatever, like you call it saying like, this guy is taking it. I don't have it anymore. Therefore, like if you try to print it again, you will get an error. Like the compiler will just, you will not get an error. The compiler will just not compile. This is useful when you don't need things anymore. You want to give it away. It's often used with postfix, very useful for things like unique pointer. Exactly. If you have a unique object, you don't want to maintain like references from multiple places. You want to just be like think like locks, would kind of make sense. Here's a lock, take it. I don't have it. So if you can do this on the language level, like let's say if you want to maintain a lock in Python, you have to write all this code to make sure multiple things cannot change it at the same time. You write really complex logic. But if you had a compiler that said that can guarantee only one thing can own this and nobody else, then it's a lot easier to just do change. You don't have to worry about the world outside. When I say you, I mean the function who took it, it does not have to think, will somebody else use this? Because nobody else can. That is the whole idea with owning and why things are kind of nice.
Is this good for message passing? So you're moving something from one place to another and say, okay, change it here, then move it to another place, change it there. So you know at all times what is actually doing the change.
It is good for
as a function.
It is good for that, but more than anything, it is good for the invariant that it introduces, which is a function like somebody else used to own this. They were allowed to make changes to it. Now I gave it away, so I cannot do anything with it. That's only that one function has the ownership to it. So when you're writing code, you will find yourself not checking from multiple places, like the value of things, you will not write this complex, gnarly code. Your code will be very simple. It will be like, you got a function, you changed it. You didn't even check if somebody else would be bothered by it. You just took ownership and then you do whatever. And that is the big benefit, really. From a code writing point, once ownership idea kicks in, then you have a really, especially think about this when you're writing a multi-threaded program, right? Now in multi-threaded program, it's very easy in languages like Python and stuff to like overwrite things from different threads. But this actually will work across threads within the same process. So if a thread took an ownership, the other thread will not get it, stuff like that. So it matters when, multiple threads of execution matter more. In Python, we don't do so much parallel stuff, but in languages like Rust and Mojo, you can easily use this for doing like exclusive parallel stuff. So this is just like, it's easier to see it in action once we start using it.
Cool.
Exactly. So when you own something, you have to make sure you should delete it. Otherwise, the compiler is like, you cannot just own things and not keep the promise of deleting it. So exactly, if you specify del somewhere, if you see the dunder del function somewhere, that most likely means that this struct knows how to own it, because you cannot delete something that you don't own. These are like, you know, details that don't matter today, I would say. I'm just putting it on the slide. Def versus function argument passing, right? Mojo def, yeah, Mojo's def is just sugaring for the function, right? So in Mojo, when you write def, what Mojo is doing behind the scenes is that it's just saying like it's just, imagine injecting these little argument type messages. So def argument without an explicit type annotation defaults to an object. When you don't give any type, then it's going to be the basic object, right? And without convention, as in out or borrowed, it's passed. So this is where I probably become like the history guy again, but passed by implicit copy into a shadow mutable var with the same name as the argument. Long story short, like we can go through the manual, look at this, but what matters is that it has exact Python-like behavior that you expect. And you don't have to like write in out or owned or borrowed or anything. It will just give you Python-like whatever you're used to in Python, it's going to give you exactly that. Requires that the type has this. Yeah, sure. Okay, I will not touch too much into this right now. We can talk about this later. More values, more, what did I say? Lifetimes. Yes. Okay, exactly. Anytime you create a value, you have to think about lifetimes. Or at least it's good to think about lifetimes. If you use the default stuff and get by, that's fine. It's very comparable to other languages. It's hinted to be even more powerful in the future. And this is the part where they said that you could even make guarantees saying that you are not allowed to move this. I created it and nobody is going to do anything else with it. And this is something like a lot of languages don't let you do right now. Even Rust does not let you do that, if I'm correct. And how we will use it, like there is this abstract language design part of it and how it's used. Let's continue. This is the part that everybody cares about, and it took, I don't know, 2 hours, 25 minutes to get there or something. But but yeah, basically, you know, like the whole idea is, yeah, if you can't beat them, join them. So, you know, you should be able to use any Python module. This is how you use it. You just say Python import module, module name. When you write let module name, and you know, it's a good idea to write let here and not a var. I will let you think why, because, you know, you don't want to change an imported module. So when you say let module name is this imported module name, this is pretty much equivalent to the Python form of import module name as this. Currently, you cannot import individual members of a module. So you cannot say from style import, you cannot do. You can only say import this module and call it this. You can say from this module, import this. But it's not a big deal, right? You can just like do a dot syntax and get access to it. Local Python modules, if you have written it in your directory, you just add this to the Python path like this, and then now you can use it.
Can I ask a question
Sure.
on this? I guess, did you get a sense from the documentation? Like, I'm assuming that like whatever the slowest language is, if you start including a bunch of your slow Python code in, like it's going to be as slow as that versus Mojo just taking that and doing something magical with it. Do you like, is Python just, is the Pythonic syntax the gateway into, do they actually want people to write in a Mojo way, or will it really be interoperable?
So I guess this is where opinions come in, and like, who knows? Honestly, who knows, right? But what their idea is that, and they're trying to, I guess, go the TypeScript way of, you know, like if we can take in all that stuff there, and then so the nice thing is that, once again, like this is the part that I don't know how this works. I don't think, and this is where I say, I don't think they're spawning a Python, you know, they're not spawning another process and talking to it. they're actually emulating Python, right? To some extent, or maybe they're not. I don't know how this works, but I would assume that on day one, like Python will just run at Python speed, and they will keep increasing underlying things. And just because Python, eventually it emits like Python bytecode, right? Now, if you can make the the representation of whatever runs the Python bytecode better without changing the Python bytecode, then you're winning. And I think that is the approach they're going for. So on day one, your Python will work, and then eventually maybe you will even get faster. I do not know this. So right, when you're in Python, when you're writing all your Python code, you do not think about memory management. You just write Python the way you would. Like you can write, for example, so you have Mojo project, you have Python like script from something else. You don't have to worry about this in out, all this stuff. Like when you do Python import module, all that stuff, Mojo will be like, this is Python, I know what to do. There's this little thing. So what you can do is, and this is kind of that threw me off, is like, what? You can also use Mojo stuff in Python. And this is kind of weird, but you can actually define a list. You can define these types in Mojo code and make it available to your Python code. We can look into the manual how. Mojo, for example, Mojo does not have a dictionary. So actually, if you need a dictionary in Mojo, you use Python dictionary. You just use the dict method, and this actually calls Python dictionary.
Wouldn't you just use a struct there? I mean,
sorry, a dictionary is really a key value store, right? And Mojo does not have one yet. So you could use an array and keep track of it in a certain way, but having a data structure where you can say, give me the content for this name I have, it does not have it yet. So you'll have to come with other tricks, but I can show you. This is more fun to look at from this way. So this is what it looks like, right? From Python interface, import Python, and then you import the module. And now you basically write everything like you're writing Python. You can print Python objects. And you can import local modules, Mojo types in Python. So Mojo, it's kind of, to me, this is really funny, but you can pass Mojo types to Python code, which is like, why would you do that? I guess they wanted to. So you import a Python module called myPython2, and this is a function written in Python, right? But at this point, you're passing all these things. These are Mojo primitives, and apparently it works, which is good because you don't want this to break, because this pretty much reads like Python here. But all these things you created, these were created in Mojo land, right? It's like allocated by Mojo. So it's good that this works. Otherwise, like it would be really annoying. And this is the part. So where we don't have a dictionary, I think my throat is starting to dry up now, but you can just use like Python dict and then mix that in your Mojo code. We're getting pretty close, guys. So you can use the dict method. And so yeah, this was like basically all the foundational concept. After this, there is a section where you can do like, where the magic actually for Mojo begins in this part. You can do what I like to say, like really fun stuff that's easy to get nerd sniped if you like programming languages. But we can talk about that later. Yeah, there's a lot more to Mojo, only scratch surface. We can continue if we want. I don't know if I can do it back to back next week. Maybe I will need some more time to prepare, and maybe people will want to play around with the code. But if we want, we can actually start doing other things, or maybe we can call it a day because it's also getting late.